Okay, we're going to do a few examples using exponential equations. Now, this exponential equation and this one are the same thing. The only difference is this is usually, they'll talk about it this way when they're dealing with financial information. But I'm going to show you it's exactly the same thing. This is the output, and this is the output. This is the money you're going to have after so many years at a certain interest rate, depending also on how much you initially put in. So it's the starting value, the factor, and the number of time periods. This is how much you have as an output. That's the starting value, that's the factor, and that's how many cycles or time periods or whatever. So they're really the same equation. I mean, you don't have to memorize them because you can write down a sheet before you take the test. So let's do this for 5 years. And so we're going to, here's our starting value. So right after 5 years, we're going to have starting value times, we're going to be increasing by 5.8% per year. So it's 1 plus 5.8 over 100 raised to the, in this case I'm going to do 5 years, but I'm going to do it this way. So this is going to be 1 plus, is going to be, when you put in your calculator, you're going to get 1.05. So that would be 1 year. If I did it again, that would be 2 years. If I did it again, that would be how much I had after 3 years. If I did it again, that would be how much I had after 4 years. And if I did it one more time, that's how much I would have after 5 years. Now, hopefully you know that a shortcut to repeated multiplication is exponentiation. So instead of doing this, what we do is simply the following. We're going to take 5,000 times 1.058, and what do I do it this way? 5,000 times 1.058 raised to the 5th power. So you can either do it this way or you can just do it this way. And so look at the equation here. So our output, which is going to be the amount that we're going to have, is equal to our starting value times our factor derived by what the percentage increase is 5 times for 5 years. So, and you're going to get and that would be dollars. So that's what that investment would be worth after 5 years. Now to change it to 10 years, I'm simply going to change this. Put that in my calculator, and you can try it. And you get $8,786. That's after 10 years. Now, and finally, I'll change it to 15 years by just changing this to 15. And I'm going to get that much money. So I more than doubled my money after 15 years, my initial investment. Okay, so here's another example, and this is kind of like, this is going to explain why states like New York and Michigan went into lockdowns over the virus. These are new cases per day, and this is the day. So when they got up to about 10,000 cases a day in New York, or in areas swaths of New Jersey, it was growing at about 16%. Now watch this, 16%. It's going to change that to 16% now. One plus R would be 1 plus 16 over 100, 1.16. Now I'm going to use this equation. This is going to be new cases every day. And this is going to be the beginning amount, which is 10,000. My rate, which is 1.16, my factor, raised to the number of days. So this is what scared the living whatever. So initial value, which I don't want to change, times my factor raised to the first power. And let me put commas in there and get rid of decimals. So they had 10,000 cases and it'd be growing at 16% a day. There was 11,600 new cases the next day. So let me run this down for 10 days. Whoops. Try it again. Run it down for 10 days. And you're seeing that the new cases is doubling about every 4 to 5 days. So it goes from 10 to 20 in 4.5 days, and then it goes from 20 to 40 in another 4.5 days. That's the doubling time of the virus, was about 4 or 5 days. New cases. So they imposed lockdown, shelter in place, and Governor Cuomo was talking on TV about this. He said, we were trying to get it down 10%, but if it goes up 2%, this is what could happen. And it doesn't look like a big difference between, okay, it's going down 10% or up 2%. Let's take a look at this. What would my factor be here if it's decreasing by 10%? Well, it's going to be 1 minus 10 over 100, which would be 0.9. So if there's 10,000 new cases a day and it starts decreasing by 10% new cases per day, here's what would happen. Y equals initial value, which is locked, times my rate, which is locked, raised to the A4. We'll drag that down. And for a whole month, and we can see that if they can get the rate to 0.9, which is below 1, which you're multiplying by less than 1, it's going to go down. This is what they're trying to accomplish. They would get new infections down to 424 a day. Now, if people just don't pay attention or follow things, it could go a little higher than 1. And that would be 2% increase, which is 1 plus 2 over 100, which is 1.02. And that's going to equal initial value, locked, times growth factor, locked, raised to the F2, F4. So this just means one person, say about 100 people, each one of them is infecting one other person. Two of them are infecting two other people. Here you got 10 people. One of them is not infecting anybody, and 9 of them are infecting one other person on average. So it's not a huge difference. We run it out for 30 days, and now we're up to 18,000 cases a day versus 10,000. So we almost doubled it again. So just a small difference here can create a huge difference in the outcomes. So now the last thing I want to do is take a look at this as a graph. So this would be an exponential graph here, and that's exponential growth, and that's at that rate that we're using, 2%. Now I'm going to switch this to 15%. And I'm going to regraph that exponential growth. You can see how much steeper the curve is, right? When they talk about flattening the curve, they talk about having it go up less steeply, right? Days down here, cases. And finally, I want to look at exponential decay. Insert a graph. And there's an exponential decay curve. When you have your factor less than 1, you're going to get exponential decay.